All right, so our next example has to do with traffic. So I'm going to zoom in a bit because this diagram is essentially everything. So you've got four intersections. Maybe this is modeled after a downtown city block, but maybe not too. It doesn't necessarily need to be. But you've got four intersections. That's what really matters here. And all the streets in this problem are one-way streets, just to keep it a little bit more simple and cut down on the number of variables. But say, take this intersection, for example. You've got a street headed south towards it. You've got a street headed west towards it. And then you've got two streets headed away from it. You've got one headed south away from it, and you've got one headed west away from it. So there's two ways, two streets along which cars can approach the intersection, and there's two streets along which cars can drive away from that intersection. And you can do the same sort of analysis for the other intersections. This one over here, you've got a street headed north towards it, you've got a street headed west towards it, and then you've got a street headed north away from it and west away from it. So the idea is you've got cars coming in and cars going out, and one of the most fundamental principles about an intersection is the number of cars that drive into the intersection not to be equal to the number of cars that drive out of it. Right? This is a fundamental principle of network flow, which is a more generalized uh, topic. But so take this intersection for example. We know how many cars are driving south towards it, and we know how many cars are driving west away from it. But what we don't know is how many cars are driving west towards it, and how many cars are driving south away from it. So, and same for the other intersections as well, right? We didn't go through this one's street by street or this one street by street, but it's the same idea, right? The number of cars driving in to each of these intersections has to be the same as the number of cars that are driving out of each intersections. Now, for some reason, whatever the case may be, somebody wants to analyze the traffic coming in and out of these intersections. And maybe they were able to set up a camera or a drone over here, and they were able to measure the number of vehicles coming out, but they weren't able to measure the number of intersections that were coming in on that same street. And the same thing over here. They were able to get a measurement over here, but they weren't able to get a measurement over here for some whatever reason, right? There's could be plenty of reasons. Maybe it's traffic area, maybe it's a safety issue, maybe there's interference, just not maybe it's just not practical to measure the traffic at one location, but it is more practical to measure the traffic at another location. But for better or for worse, whatever the case may be, this is the information we have. But what we would like to know is what would the values of x1, x2, x3, and x4 have to be in order to make sense of the data that we have. In other words, what would the values of x1, x2, and x3 and x4 have to be in order for all these intersections to have the same number of vehicles flowing in as they have flowing out of them. By the way, I skipped over this part. Let's go through it a little bit more carefully. It says that these are traffic rates in particular, right? Measured in vehicles per hour. So in one particular hour that goes by, there's 200 cars that drive south towards this intersection, and there's 300 cars that drive west out of that intersection. So X1 and X2 are also rates in vehicles in that particular hour, right? So that you can think of them as in number of vehicles that went in a particular hour, either in or out of the intersection, depending on the case. And same with X3 and X4 for this intersection and this intersection. Okay, so the way we're going to do this to figure out what all the variables would have to be is just like in a previous example, we're going to set up a system of equations, and we're just going to look at one intersection at a time and use the principle that we just mentioned, is that the number of cars that enter it should be the same as the number of cars that leave it. So let's start with this first intersection up here. So the number of cars that enter that intersection can be written as x1 plus 200, right? And the number of cars that exit that intersection can be written as 300 plus x2. Notice this is already a linear equation that's not formatted the nicest, but let's just worry about writing all our equations down first, then we can format them after. So now the second equation, let's move on to the second intersection. What do we have here? So the number of cars that enter that intersection is going to be x4 plus 100, right? And then the number of cars that leave the intersection is going to be x1 plus 100. So that takes care of the second intersection. What about this one down here? We've got x2 cars entering the intersection, and we've got 200 cars over here entering the intersection, and then there's 400 leaving this way, and then x3 leaving to the east. So let's write down an equation that describes that. So we've got x2 plus 200 is equal to x3 plus 400. And then lastly, we've got one more intersection. We've got x3 coming in and 500 coming in. Then we've got x4 leaving and 200 leaving. So we can turn that into an equation as well. And we can say x3 plus 500 is equal to x4 plus 200. Okay, great. So that is a system of equations that we want to solve. So what is the first step? First step is we want to organize everything, right? We need to collect like terms, get everything over to the left-hand side of the equation so we can line up all the variables in terms of columns and set up our augmented matrix. So this is going to give you x1, the first equation. I'll move everything over to the left-hand side. x1 minus x2, and it'll leave some space for x3 and x4, even though they don't appear in this equation. And I'll have 300 minus 200 is going to be 100. So moving the constants over to the right-hand side. Okay, so then over for our second equation, if I move the x1 over here, I'll have x1. There's no x2 or x3, but there is an x4, so I'll have plus x4. And then if I move the constants all to the right-hand side, I'm going to have 100 minus 100, which is going to give us 0. Okay, so then now the third equation, we're going to have x2 minus x3 on the left-hand side, and then 400 minus 200 on the right-hand side. And then our fourth equation, we're going to have x3 minus x4 is equal to negative 300. Oops, that's not the greatest bracket. There we go. So that's the rewritten version of our system. So great. Now we can write down an augmented matrix more naturally. So what is the augmented matrix of this system? I'll put it right here. So we've got first equation is 1, negative 1, 0, 0, 100. Second row is negative 1, 0, 0, 1, 0. What's the third equation? We've got 0, 1, minus 1, 0, 200. And we've got 0, 0, 1, negative 1, negative 300. Okay, so that's our augmented matrix. And just like with the last example, because I'm more interested in the applications for this section, I'm not interested in going through a whole bunch of row operations and going through Gauss-Jordan elimination method. I know you guys can do that now, and I invite you to go along and use the same tool that I'm using, the website I used in the previous example. But this is what it will reduce to. You'll end up with this is the reduced row echelon form of the matrix. You'll have that as your first row. Your second row will be 0, 1, 0, negative 1, negative 100, 0, 0, 1, negative 1, and negative 300. And then the last row is actually all zeros. So actually, this linear system, you wind up with a free variable as well. So x4 is going to be a parameter. Okay, so x4 is going to be a parameter. What does that say about the other three variables? Let's solve for this one. So this is going to be, if you solve this for x3, you're going to get x3 is equal to s minus 300. Okay, and take a look at this pivot row. You're going to get x2 is equal to negative 1, s minus 100. And then lastly, for the first pivot row, you're going to end up with x1 is just going to be equal to x4, so you're just going to get s. Okay, so now we can put our solutions together. Our general solution, I'll write it as x as a vector, and then the four variables, we've got x1, x2, x3, and x4. So let's put everything together. So x1 is s, x2 is s minus 100, x3 is s minus 300, and x4 is just s. And is there any restrictions on our parameter s? Well, take x2 for example. It's s minus 100. So if s were equal to, say, 50, then x2 would be negative 50. How would you interpret that? If x2 is set to represent the number of cars that drive out of the blue intersection, well, if x2 is negative, that would mean, the only sensible way that I can think of to interpret that is that there was 50 cars going the other direction. But that doesn't make sense here. That's not feasible because remember, these are all one-way streets. So that allows us to make a sensible judgment call here and say, okay, we need x1, x2, x3, and x4 to be positive. So not only do we need s to be positive, we also need it to be greater than or equal to 300. It doesn't need to be positive strictly, it can't be negative. It's certainly reasonable to have some of these variables equal to 0, but just not negative. So let's say where s greater than or equal to 300, and also it should be an integer, right? It should be a whole number. We can't have, say, 300.2, because you can't have part of a vehicle go through the intersection, or if you do, then there was probably a pretty nasty car accident. But that's not what we're talking about here, right? We're talking about numbers of vehicles. We're counting vehicles, not measuring them. So we should say is an integer. Okay, so that is the general solution. So again, it was an underdetermined system. There's no way to know exactly, based on the information that's given, exactly how many vehicles were going in and out of every intersection. But you're set up now so that, let's say somebody else says, oh, by the way, that footage that we had where we counted the vehicles coming north from the Brown intersection, we thought we had lost that. We thought that camera had been destroyed or lost, but it turns out we found it. So we actually know that x4 was equal to 57. Like, let's just say that happened. Then you could instantly say, or not 57, because that's not a reasonable answer. Let's say you found out that, oh, by the way, it turns out we now know that x4 was 357. Then you could say, okay, great. That means we instantly can tell you what the other three variables must be as well. So this is the best you can do given the information you have.